but with a much smaller mass, the effect would have been the following. You would not have had an amplitude like this. You would have had a sine wave. You would have had the same period on that sine wave, but it would have been a very low amplitude curve. So the amplitude of the curve is due to mass. This then is one example of one such star. Here's another star with one planet around it. Notice the curve that fits that. Notice immediately you see it's not a sine curve at all. It's something much more complex. Stars going away from us, away from us, away from us, away from us. Whoa! Comes by it, coming toward us, 200 meters per second toward us. It changes direction. You can see how fast it changes direction. It comes toward us at about 200 meters per second, slows down, starts going up, slowing down, and then going away from us again once it crosses zero. What kind of an orbit is that? It's an elliptical orbit. An elliptical orbit. Yes, it's an elliptical orbit. The amplitude of this also conveys information about the mass of the minimum mass of the planet around that star, and that one is about minimum mass about 5 Jupiter masses, and it has a period. Notice the time scale here is in years, so this has a period of almost 1,200 Earth days. A very distant orbit, 1,200 Earth days, almost at a Jupiter-like position in our solar system.
The change in the orbit, in the approach and recession is related to the relative masses of the objects.
Yes, the relative masses of the star and the planet.
We can't get absolute numbers at that point, can we?
We can't. That's correct. The question is a very good one. Can we get absolute masses using the Doppler method? And the answer is no. One, because although this is a G2 star, and the spectral types of stars are known to have a narrow range of masses, there's always some uncertainty about the mass of that star. So it's not perfect. In addition, and more importantly, is that the plane of the orbit, and therefore the plane of the wobble that you're observing, is not known either. The way that the mass would be best constrained is if you, as the Earth-based observers, were looking at a wobble which was in a plane directed right at you. Stars coming toward you, away from you, toward you and away from you. As long as it's coming toward you, you're getting the full vector. But if the plane is tipped this way, the star is going to be wobbling toward you, away from you, and toward you and away from you. But you're only getting a small component of the total wobble speed. And therefore, what's mentioned here is m sine I, the true mass of the planet, times the angle of the inclination of the the wobble plane to our observations. So it's an m sine I thing. So these are minimum masses. Here's another star. I've set you up now for this. 1988, okay, time, again along the x-axis, but we're looking from 1988 to about 2003. Of course, observations continue. And the velocity, Doppler measured velocity here from 0 to minus 150 meters per second and plus 150 meters per second. Look at these data.
Messy.
Were the astronomers on something? What a mess. It looks like a dog's dinner. It's awful. Or could it be, or maybe not your dog's dinner, but
His dog dinner.
Notice the complexity here. The uncertainty on the first note. Is this just poor data? No, it is not poor data at all. What you're seeing here are the data, the values are about the size of the points themselves. The uncertainty on each of those points is about the size, the vertical height of those points themselves. So the data themselves are good, and that star is in fact doing what you're seeing it doing there. It's really very complex motion.
More than one planet.
More than one planet is involved. That's exactly what's involved. Is we're looking at an interplay not of a star and a single planet, but a star's complex wobble because of the gravitational interaction of at least 3 planets orbiting this star. This star has at least 3 planets. Can be pulled out of the data here for three planets.
The planets have to be considerably massive to see this, right?
Correct. So the planets have to be quite massive to be seen with this method, and that gets me to another point. For example, it's a very, very good point. The minimum masses that can now be observed are about a third of a Jupiter mass, maybe a quarter of a Jupiter mass can now be measured. Jupiter in its current position, our Jupiter, how much motion does our Jupiter have on our Sun? It's about 12.5 meters per second. Our Sun wobbles with a speed of just about 12.5 meters per second as a result of the motion of Jupiter being there. How much does the Earth contribute? Earth contributes to the Sun's complex motion. But how much does it contribute? Earth contributes 8 centimeters per second of motion, of wobble to the Sun. So here's the upshot of it. Consider then that if 2 meters per second is what is currently detectable, measurable, 2 meters per second. If there's anybody else out there with a technology comparable to ours now, they already know that this place has at least 4 substantial planets: Jupiter, Saturn, Uranus, and Neptune. They already know it. Or are close to knowing at least 3 of them, maybe 2 of them at least, but their methods are capable of detecting the outer 4 big ones.
How do we know that the wobble that we're seeing is from just 4 planets or more planets?
Yes, how do we know it's just 4 planets and not greater than or equal to 4 planets? We don't. The data are only consistent at the present time with 4 detectable planets. There could be more, absolutely. And that's why, of course, getting more sensitive methods at 55 Cancri, for example, would be so exciting. Is it limited to only 3 or 4 planets around that star? Or could there be many more? Good point. 3 confidently inferred from those data now, 4 suspected, and can't detect others that might also be there that are smaller or in much further out with longer term orbits. But stay tuned. Data are coming in all the time, as you know, and our ideas evolve as the data come in. So good point. Minimum 3, possibly minimum 4 planets around that star. Here is a kicker. This is a kicker.